Okay. Um, well, we don't seem to have many people up in Hattiesburg, so I'm not sure what's going on with that. Um, but I guess this is what happens when I put all the lectures on YouTube. Um, now, um, I hear a lot of noise down at the coast.
There's three of us.
Okay. Oh, well, 60%. That's better than we're doing up here. Looks like. um, okay. Now, and recording. One thing I want to point out is um, midterm grades are. I had to report them. Um, dang it. This Friday. We don't have a lot of grade information just yet. So, um, homework 2 is the assignment that I've gone through and graded. So now a midterm grade is an unofficial advisory grade anyway, so it doesn't really carry any actual weight. But so when I put in your midterm grades, it's going to be off of that because that's the only assignment I'll have completed by then. Um, so um, so because this week is the last week for students graduating in December to or graduate students to defend any theses, and I have one such student. I haven't had a chance to continue grading, but I will be getting to homework 3 soon. I generally wait until roughly 2/3 or so of a class has submitted an assignment before I start grading it. So get them in sooner, I start grading them sooner. Um, and we never did hit that threshold with homework 1, so I'm not sure what's going on with that. If anyone has not submitted homework 2, so there isn't a grade at this point, that's something you should deal with. I'll fill in something. I have to fill in something for an interim grade. I prefer to not fill in an F, but these things should be gotten in if they haven't been already. Because I know there's at least some homework 2s that are still missing. Okay, okay. And then look at the calendar for what's coming up. Okay, so we're here on October 8th. So it is 2 weeks from today is the midterm. But the exams in this class will not deal with MATLAB details. So it deals with problems that can be worked out on paper. I still need to produce a the actual exam as well as something for practice. So I will try to get that going within the next few days. Hopefully by Monday or so, I'll have that up. Okay. You're welcome to remind me if that hasn't happened. Okay. And then as far as what it'll be on, there'll be questions from Chapter 2 on error analysis and computer arithmetic, and there'll be some questions from polynomial interpolation as well. Not this section, 7.5, but the stuff I'm covering this week. So whatever I cover this week on polynomial interpolation is the last material that is fair game for the midterm. Okay. Okay. Now, okay. So, let's see. So I'm going to cover divided differences, Newton interpolation today, and then if there's time left over, then we can deal with homework questions. I have gotten some questions on homework 4 on interpolation, and that is so I've started filling in the questions page on that. So again, be sure to check that. Okay. Now, so to recap where we're at, so the problem that we've been considering is really the focus of pretty much the whole chapter is given points in the plane n plus 1 of them, so numbered from 0 to n. Find polynomial of n, degree n, that passes through these points. Okay, and so far we have some approaches to coming up with this polynomial. So and I'll explain what is wrong with them. Okay. So the first approach that was covered was solve system of linear equations in power form, which is the standard form in which polynomials are typically written. Okay. This should be a n x to the n. Okay. So the drawbacks to that approach is costs order n cubed operations, and solving an ill-conditioned system, so sensitive to changes in the data, if the x's are clustered together, if any of the points are close together. So this approach doesn't work well. The main thing is the lack of efficiency. Actually, let me zoom in on this. Okay. And then the second approach that was covered last week, LeGrande interpolation. So the polynomial has this form, where you multiply your y values times LeGrande polynomials, where these polynomials satisfy, if you plug in any given x values, and 0 if I is not equal to j. So it has the effect of selecting the correct y value. Now, this requires n squared operation, so a big improvement over the first method. But evaluation at any given x is expensive. So that also takes order n squared operations. So should use what's called barycentric interpolation. So that's something that's the subject of a couple of homework problems and that I covered on last week. So another problem is the following, that I didn't mention last time, but is a key focus today, is what if new interpolation points, so for example, xn plus 1, yn plus 1 are added. So, like, if you add one, you may add more, but starting with this point, if it'd be numbered n plus 1. So the problem is all Lagrange polynomials must be recomputed. So if I go from degree n to degree n plus 1, all these Lagrange polynomials that I formed, I have to rebuild them because each one of them gets modified. I have to tack on new factors, linear factors, to account for the new point. I also have to form a whole new Lagrange polynomial. So another way of putting it is this method of Lagrange interpolation is not progressive, meaning that if you increase the number of interpolation points, you don't really have the ability to reuse much. You can to a point reuse work you've done, but it's not really great about it, especially compared to the method I'm about to show you. Okay, so what we can do instead, use what is called Newton interpolation. So the polynomial, it's going to be the same polynomial, because if I have these n plus 1 points, and I'm forming a polynomial of degree n that passes through them, that polynomial is unique. It has nothing to do with the method you use to get it. We're still chasing one polynomial. So these two Pn of x's are the same. But we can always choose to represent it in a different form. Here we have two forms already, and we're going to introduce a third one. So whatever form you're using is conducive to a certain method of computing it. So to get the Newton form of Pn of x. So what does that look like? So we have a sum, so some coefficients times these polynomials, which I need to define, where, I'll do it this way. So the first polynomial, n0, is just 1. So your leading term is just a constant. And then the next one is just x minus x naught, so linear polynomial. And then it goes up in degree from there. So it'll be x minus x naught, x minus x1. So that's going to be a quadratic. So whatever subscript we have here indicates the degree. And in general, what we have is, okay, so x minus x naught, x1, all the way up to x minus x j minus 1. Okay, so important thing is nj of x is always of degree j. So we have coefficients times polynomials of increasing degree that all have this form. Okay. So if we're stipulating that Pn of x has this form, then it's these coefficients that we need to figure out. So those are the unknowns, which in a way is kind of similar to this approach. Instead of using Newton polynomials, we have a monomials, 1, x, x squared, and so forth, all of increasing degree, unknown coefficients. But the way we can get these coefficients as c's is going to be a lot faster than what it would take to get these a's here. Okay, so now what I need to do is talk about these coefficients. So and that's where these are called the divide differences. So the coefficients of the Newton form divided differences. So the notation for a divided difference is this. So the function, okay, so Newton form of, dang it, I want an actual dollar sign, not, I want math mode. Okay, Pn of x for interpolating y equals f of x. So that's important. That yes, we're still dealing with n plus 1 points in the plane, but now we're assuming that these points are coming from some function f of x, which we can assume anyway. But I'm making it explicit. So the notation for divided differences is a function you're interpolating, and then in square brackets, dang it, hold on, xj. So that's the notation for a divided difference, that it has a certain x value specified. Now, I need to give the actual definition of a divided difference. Okay. So just like with the Newton polynomials themselves, that's best done by starting with the lowest degree and working up from there. So the lowest order divided differences. So we only have one x value between the square brackets. Well, that's just a function value itself. So we're just plugging in this x into a function. Okay. Next, if I have two x values in here, then that's going to be, this is where the term divided difference gets its name. So I have, up top I have xj, f of xj, and then xj plus 1, and down below I have xj minus xj plus 1. Okay, so it is so we have two differences that are being divided, thus divided difference. Real imaginative. The order of the points is actually irrelevant as long as you're consistent. So if I have xj followed by xj plus 1 up top, and I have the same ordering down below, so as long as you do that, that'll be correct. In general, when you have however many x values in here, rearranging the order of the x values does not change the value of a divided difference. Okay, now, so what I have here with one x value, that's called a zero order divided difference. Here we have 2 points, that's called a first order divided difference. So how do we do higher order divided differences? What you do is, so I'll do one with 3 points. Okay, j plus 1, j plus 2. Okay. So what we do for that is also a divided difference where, okay, I plus 1, x, I plus 2, okay, minus, okay, x, I plus 1, okay, over, and then I have x, I plus 2, That's xi. Okay. Actually, for consistency, like I said, since the order doesn't affect the value, I'm going to change the order of a previous one just so it's consistent. Okay. Oh, sorry, I have j's on the left and i's on the right. Need to make that consistent too. Okay. So notice here I had 3 points as the arguments to my divided difference. So here I take the lower order divided difference consisting of the last two. So in this one, I leave out the first point and compute that lower order divided difference that comes from this. And then here I leave out the last point and compute that divided difference of lower order. And then notice I'm dividing by the difference of the extremal x values. So the last point minus the first point. Okay. So then it would just go on from there. So more generally, if I have a divided difference of order k, all right, so if I start from xj plus 1, xj plus k, and then I'll have this difference quotient. All right, so I'll have xj plus k minus xj down below. And then for divided differences, up top. So I'll just copy and paste these and fix. Okay, so in this first one, I leave out the first point. And in this one, I leave out the last point. So xj plus k is gone. We stop at xj plus k minus 1. And again, dividing by the difference of the extremal x values. Okay, so this recursive definition allows us to readily compute all of these divided differences that we need from a Newton polynomial. So first, what I would do is I would take all my y values and plugging in all these x's into f, and then computing higher and higher order divided differences from there. So divided differences of order 0 are just the y values, and order 1, order 2, etc., until I get to my jth order divided difference. It gives me the last coefficient cj, and then I'm done. Okay. Now, what I will do momentarily is give a nice systematic algorithm for computing divided differences. So it's one that you can either carry out on paper, or the algorithm is given in the book. And one of the homework problems for homework 4, or homework 5 rather, is writing a MATLAB function to implement that given algorithm. Okay. Now, once we have the divided differences, we can get our interpolating polynomial as follows. So I have Pn of x. Well, I better do it this way. Okay. So I have f x0, so our first 0 order divided difference, plus f x naught x1 times x minus x naught, plus, and then it keeps going. All right, so I'm going to have x minus x naught, x minus x1, and What is that?
Sorry.
Okay. We have startled people up here. Okay. So then it goes up to the last term, so divide difference involving x naught, x1. Actually, I'll put in the last two terms. So up to xn minus 1. So there's a divide difference of order n minus 1. So I have x minus x naught, x minus x1, up to x minus x n minus 2. So remember, whatever x values you have in your divided difference, you have one less in your linear factors that follow. So this is a n minus 1 order divided difference, and is the polynomial degree n minus 1 also. And then the absolute last term, okay, the n4 divided difference, actually I'll put the plus here for uniformity. Okay, x minus x naught, x minus x1, x minus x n minus 1. So that the last, so this last term is polynomial degree n, which the overall polynomial is supposed to be. Okay, so we just take those coefficients that we get from divided differences and fill them in here, and it can form our polynomial. Now, notice the difference between the last two terms. All we have, so first of all, we have a divide difference that's order 1 greater, because we're throwing in another point, xn. And we have the exact same linear factors in both terms, except we have this one tacked on to the end of the nth degree term. So what I want to point out is the first k terms, I should say k plus 1 terms of Pn of x form Pk of x, the interpolating polynomial of your function f of x, whatever that is, at the first k plus 1 points, x naught, x1, xk. So this is the key difference between Newton form and Lagrange form. So suppose I have Pn of x, and now I decide I want to interpolate my function f at one more point. So I can keep this entire polynomial. The only thing I have to do is add on one more term. So it means extending Pn of x to Pn plus 1 of x requires only adding on this term another divide difference with a new point thrown in there. So this is an n plus 1 order divide difference. And then these same linear factors multiplied together so the same ones I had before in this last term, and then one more, x minus xn. Okay. So the Newton form is readily extensible when new interpolation points are added, whereas Lagrange is not. Lagrange, you do add on one more term, but you have to go back and fix the previous terms. Not necessarily Newton form. All these terms would be completely unchanged. Okay. Now, so what I need to give you at this point is a practical procedure, what you can code up or carry on paper for actually obtaining the divided differences. So the idea is you fill in what is called a divided difference table. So I'll talk about the process as if you're going to be carrying it on paper. And yes, that will be a question on the midterm. I can promise you that. So I'll just give that away right now. And then I'll talk about how this will be done, like from a coding standpoint, because that's something that comes up on the next homework. So what is the divided difference table? So you fill it in column by column. So first column has the y values. So that's, in other words, your zero order divided differences. The second column has first order divided differences. F x xi xi plus 1 for all right. So here in the first column, we're going to have n plus 1 values. Second column, we're going to have n values. And we're going to keep going. So each column, as you go from left to right, so the idea is, so I should say first leftmost column. So you're going to go from left to right, computing fewer and fewer values each time. And to go from one column to the next, you use the recursive definition of divided differences, this one, where you're taking two divided differences from a previous column and subtracting them, and you're dividing them by differences of x values. So you can just keep filling in the table. So you keep going until only the n plus first column has only one value. And that's f of x naught up to xn, the n4 divided difference. Okay. So now I'm going to illustrate this procedure with an example. Okay. 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 So first, the data, which I used from a previous example. All right, so x naught is minus 1, x1 equals 0, x2 equals 1, x3 equals 2. So those are my x values. And then my so my function values. So f x naught is so f of minus 1 equals 3. fx1 equals f of 0 equals minus 4. fx2, which is f of 1, which is 5. And f of x3, which is f of 2, is minus 6. All right, so that's all my data. So I have 4 points, so I'm finding a cubic polynomial, degree 3, that passes through these 4 points. Okay. Now, all right, so my divide difference table is as follows. Okay, this is going to be interesting to try to fill out on the fly in LaTeX, but I'll make it work. Okay. Well, actually, the visual representation would be too big to hold a computation, but okay. Let's see, how much room do I have on the page? All right. So, So you're going to have 4 columns altogether. Okay. Let's see. So to get the spacing just right, I'm going to need 7 rows. So my first column will be my y values. So I'll fill those in first. I'm filling in a empty matrix to hold all these things. Then I'll have 7 rows. 1, 2, 3, 4, 5, 6, 7. Okay. So now fill in x1 is minus 4. F of x2 equals 5. And f of x3 equals minus 6. Okay. So I have my first column filled in. Now, when I go to my second column, actually what I'm going to do well, I'll fill these in first, and then I'll talk about how to compute them. Notice I'm putting them in between. That's intentional. Because, like I said, each column has 1 less value than before. So the divide difference table is actually staggered. So, and plus, this value, fx0, x1, depends on these two. This one depends on these two. So each one depends on the 2 values immediately to the left of it. So that's reflected in this staggered way in which I've arranged them. Now, for convenience, even though I said this is the first column, I'm going to put another column to the left. To hold x values. Whoops. Okay, so the x values, I'll have x naught is minus 1, then x1 equals 0, x2 equal 1, x3 equal 2. Okay, so now what I'm going to do is to get fx0, x1, so I'll just be doing literally divided difference. This minus this divided by this minus this. So I'm going to have, for this value, I'm going to have minus 4 minus 3 over 0 minus 1. Okay. So again, this minus this over this minus this. So working all that out will give me minus 7. Okay. Then I move to the next. 5 minus a minus 4. So that will give me 9. Over 1 minus 0, which is 1. So I end up with 9. And then finally, the last one right here, minus 6 minus 5. So that's minus 11 over 2 minus 1. So that's going to give me minus 11. Okay. Are there any questions about how these last 3 values were obtained? So you can carry this out on a test. Okay. All right. Now, to save space. Okay. So now I work with these 2 values to get my next divide difference. That's going to be of second order. So let me fill in where that goes. So that'll be fx naught, x1, x2. I need an f in front of that. Okay. And then down here, f x1, x2, x3. Okay. So this will depend on these 2, this will depend on these 2. What's a little less clear is, what about the denominator? Which x values do I subtract? Now you can could consult the definition that I gave, but that's pretty cumbersome to do mentally. It'd be nice to understand visually where it comes from. So the numerator is more straightforward. So I have that 9 minus of minus 7. So the numerator will be 16. But what about the denominator?
5 minus 3.
What?
Would it be 5 minus 3 because your greatest x2 minus x 0?
Oh, but the second thing you said is correct, but not those numbers, because 5 and 3 are y values.
Oh, I was looking. Okay.
Yeah.
I was looking at the y value. Sorry. 1 minus negative 1.
By the way, the first few times I taught this class, I did that too.
Okay.
So if you think of this as a tip of a cone, and you backtrack through the cone, and you wind up here and here. So 1 minus a minus 1, so that would be 2. So we get 8 for that divide difference. And then down here, same idea, minus 11 minus 9, which is minus 20. And then you go back through the cone, so up to here and here, but you look at the x values of 2 minus 0. So that's minus 10. Okay, this was 1 minus 1. Okay, it gives you 8. Okay. Is there any questions about those divided differences? Lastly, so the remaining column, x0, x1, x2, x3. So we have minus 10, minus 8, so minus 18, and then you go all the way back. Last x value minus the first. So it's going to be minus 18 divided by 3, so that'll give you minus 6.
Wait, which ones?
Okay, so last minus first.
Last.
X value. So, hold on, let me write it out. So, minus 10, minus 8, over 2 minus, I'm running out of room. Wait, let me shorten this. Yes. Okay. Wait, that equals minus 6. Yeah, so previous two y values up top, minus 10, minus 8, and then go all the way back, like, again, tip of a cone. Follow the cone to its base. And you get 2 from there, and then go up, and you get minus 1.
Inside the bracket.
What?
But inside the brackets, you would always use your first number in the brackets and your last number in the brackets. Beside that.
Yeah, like these x values that you see here, yes, they tell you. Yeah, like here, I have x0, x1, x2. Yeah, I use x0 and x2.
First one and last one.
Yeah,
Brackets.
yeah,
Brackets.
right. Yeah, here I use x0 and x3. What I mean by the cone, which, okay, I admit I've never used that metaphor before. Like, okay. So, if you think of, or a triangle in a way, that if you think of all these entries forming a triangle, this is one vertex of a triangle, so you go, and this is the base. So follow the edge, follow this all the way to the left. And that's what leads you to the first point in this case, and the last point in this case. Another example that might, here, in computing this divide difference, you go along diagonals. That's another way to look at it. So I backtrack along this diagonal, which takes me to x1. Backtrack along this diagonal takes me to x3, and those are it's the x values that I use. I'm sorry, I cannot hear you.
It's also just the x1 and x3 are the.
The first and last.
Okay.
Yeah. Okay. The thing is, you might not have these in front of you, because I mean, you can go ahead and write them in yourself.
Yeah.
So I was trying to look for a purely visual way to see which values you use. So like, you think of it as these values, if you backtracking along diagonals, you can always get to the right ones. So,
Going up the diagonal.
whatever works. What? The trouble is, what I like to, I don't have any effective way to draw this on my screen. So, because what I would do is I'd literally draw a line along this, but I can't in this program. So, okay. I'll show you after class. Okay. Any questions about how this divided difference table was completed? All right. Now, finally, to form the actual interpolating polynomial, which is p free of x, it's cubic. So that's going to be. Oh wait. Okay. So p free of x is going to be now. So what you do is, once the whole divided difference table is filled in, remember the coefficients are fx0, fx0, x1, fx0, x1, x2, and so in other words, use the top row of the divided difference table. So these coefficients, 3, minus 7, 8, minus 6. So everything along that top slanted row is what you use. So first one, 3, gives the constant term. So it sits there by itself. Next term, minus 7, multiplied by x minus x naught. Third one, 8. So that's multiplied by x minus x naught, x minus x1. And finally, the last one, minus 6, x minus x naught, x minus x1, x2. Okay. So then you go ahead and fill in those x values that you're given, and then you can form a polynomial from there. But what I need to show you is, once you have a table, you have all these coefficients, but you only use certain ones. So top row will give you this form, which is based on the form of a Newton polynomial I gave earlier using these polynomials. Now, I should point out the divided difference table actually has some flexibility. You don't absolutely have to use the top row. You can use the bottom row, but you have to be careful about these linear factors. Those would not be the same. So the same polynomial is given by going to the bottom row, again from left to right. So minus 6 down here, constant term, and then plus minus 11, so I move to the next one, times not x minus x naught, but x minus x3. Okay. If I move to the next one, minus 10 times x minus x3, x minus x2. And finally, the last one is minus 6, x minus x3, x minus x2, x minus x1. Okay, so if you were to multiply these out, you would get the same polynomial in the end in power form. Okay. So the reason I point this out is, if you, what happens if I add another point to my data? So I have to add another x value here, another y value here. If I add the new values at the bottom, Then I keep all of this, and I just have to fill in something below, here, 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 and then there'll be another column out to the far right. Then, if I'm using the top row, I keep these terms, and then I add on one more. Whereas if I added the new x value at the top, then I have divide differences to add, here, 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 and out there. And then I would, it's best to use a bottom row representation because that's the one that's more adaptable. Again, it's the same polynomial. You could do it either way. But either way, you have a chance of reuse of most of your information. Okay, so you have a question like on a test, let's say, hint, hint. Here's your x values and y values. Right, come up with your interpolating polynomial in Newton form. First thing you do, make your divide difference table, fill it out completely. Then you can take, for instance, the top row of coefficients, multiply by the proper linear factors. Note how they progress. Constant term, first x value, first two x values, and so on. The last term is every x value except the last one. Notice there's no x minus x3 term anywhere in this first form, because that would give you something that's too high in degree. Okay. Interesting, got a quiz submitted by someone who's not here. So, go figure. Well, at least someone's doing something for this class, whether they're here or not. So are there any questions about this process, about coming up with a Newton polynomial? All right. Now, what I've shown you is good for like working this out on paper to come up with a polynomial. But what's a practical way to do all this in say in MATLAB or whatever programming language you'd like to use? Okay. So actually, I'm going to point out two algorithms that are in the book that you would use. Okay. Okay. Hold on. Like the way this is scrolling, it's kind of annoying me. Okay. And actually, this is like a preview of two of the homework problems from this section. Okay. So here is the algorithm for filling in a divided difference table. Now, since the divided difference table I showed you has rows and columns to it, it makes sense to represent a divided difference table as a matrix. But you only need a triangular matrix. It's really only filling in half a matrix. And that's what's shown here, that this algorithm fills in a matrix D of all the divided differences. And notice, so the first index is a row, second index is the column. And we number the columns from 0, indicating what order divided difference it is. So, very first thing you do, you have a loop, fills in the first column, so of 0 order divided differences that are just the y values. Then you go from one column to the next. So from first order divided differences all the way to nth. This inner loop fills in that column, column J. And notice each divided difference, Dij, relies on two divided differences from a previous column divided by the appropriate x values. Now, once that is complete, now notice that I goes from n all the way down to j, and so that means that I is greater than or equal to j. Now, what that means is whenever you have a matrix where the only entries you have are when the row index is greater than or equal to the column index, that means the matrix is lower triangular. So, in other words, the bottom half of this matrix that's below the diagonal is filled in with divided differences. The part above the diagonal is left to be 0. Okay, so this algorithm will fill everything in for divided difference table for you. Then at the very end, you don't want all the divided differences. You just want, for instance, the top row. Well, the top row would be the main diagonal. So this last loop takes the entries from the main diagonal and stores them in a vector C. So a vector C is the final output of this algorithm. And so your function that you write for the homework will behave in the same way. Now, the thing to keep in mind is, here we use zero-based indexing because that's how divided differences are indexed, and the x values are indexed. But MATLAB indexing is one-based, so your loop would go from like 1 to n plus 1, where n is the degree of the polynomial. So be careful about indexing. And what I would strongly suggest is when you implement this algorithm, like when a homework problem comes up, test it on the data from the example I just gave, which is reproduced. It's on the next page in the book. Try it on these x and y values because it's indicated. So let me fix the scrolling here. Okay. Here's your divided difference table, one I just worked out. So that way you know you're getting the right values. Okay. Test your code. Because if you don't, I will. Okay, so this is how you would code up doing divided differences. So a lot of nested loops involved. Okay. Now, once you have a divided differences, then there's a second algorithm, this one, nested multiplication, and its job is to evaluate the Newton polynomial at a given x. So here you're given the x values, and you're given the divided differences. So that's enough information to put the polynomial together. Now this algorithm does not construct the polynomial. All it does is it evaluates it at a given point. Now, if we go back to the polynomial that I've written out here, okay, so this polynomial right here. Notice, okay, actually I'm going to make a copy of this. Oh, actually, no, I'm going to use a more specific one. Okay, this one right here. So use algorithms 735 and 733. Okay. Now, what is so algorithm uses nested form for efficient evaluation. So this is a very important algorithm for a rather mundane task of evaluating a polynomial. You might think, oh, well, evaluating a polynomial is easy. Well, yes, it is. But you want to save floating point operations if you can. So So if I reproduce, whoops, where'd it go? I need this polynomial right here. So I can take this one that's written in Newton form, okay, so notice every term in this polynomial except the first one has a common factor of x minus x naught. So what I'm going to do is I'm going to factor that out. So I'll get rid of it everywhere else. Okay. Now, look what I have in square brackets. I have a constant, and then the terms that remain also have a common factor, x minus x1. So now I'll factor that out too. Okay. All right. So now the polynomial is written in nested form. Now, why does that help? Because here's my evaluation steps. So first we have I'm basically going to flesh out the nested multiplication algorithm. So first I set my y value, which is my result, equal to the last coefficient minus 6. Then I say y is equal to y, whoops, wrong place. Okay, y is equal to y, stop that. Okay, this is being really annoying again, stop it. Okay, so y times x minus x2, and then I have y is equal to, so now y is equal to this part. So now I add on the 8. Then y is equal to what's in the inner square brackets. Now I multiply that by x minus x1. And then I add on the minus 7. Then I multiply all of that by x minus x naught. And finally I add on the 3. And that's it. So if we look at the operations that were performed, only 3 multiplications were needed. So whatever the degree of a polynomial is, that's how many multiplications are needed. And this is the best way to minimize the number of multiplications. Whereas if we go back to this form, if I don't bother factoring, how many multiplications do I have? 1, 2, 3, 4, 5, 6. So a lot more. So the order of multiplications, the number of multiplications is order n squared if I leave it in this form, whereas only n, so a whole order of magnitude less if I use nested multiplication. So that's what leads to this factored form, factoring out as much as you can, is what leads to this algorithm, nested multiplication. Notice we carry out n plus 1 steps. N iterations in this loop, and we have 1 multiplication, 1 addition. That's it. So nothing to it. Well, okay, two additions. There's this addition here and this subtraction. But I should point out, as arithmetic operations go, multiplication and division are much more expensive to carry out in hardware than addition and subtraction. And if you think about it, in addition and subtraction, once you have the numbers lined up correctly, if you have n bits in your number, or only order n operations are performed. But if you think about multiplying, and if you broke out numbers by individual digits, you have to combine each one and distribute. So it's order n squared in the number of bits. So that's why you definitely want to reduce multiplication. So if there's a way to carry out a task using additions rather than multiplications, you definitely want to do that. And it can really, and you might think, oh, all these operations are so fast. Why does it matter? But the thing is, because computers are so fast, people want to perform tasks that are more sophisticated that require trillions of operations. That's how you get all the sophisticated animations you see in movies. People demand more realism, and that's why these things still matter, just as they did when computers were first invented and were a lot slower. Okay. So it's those two algorithms together that will allow you to efficiently construct and evaluate the interpolating polynomial in Newton form instead of Lagrange form. So the problems I assigned in MATLAB for this section are ones that actually are about implementing these two algorithms. So that you can. So in the current assignment, you're doing Lagrange evaluation using barycentric weights. So next homework going to be Newton evaluation. So notice that the way the function is called is exactly the same. So in fact, once you have both of these, you should be able to call them on a given x and y and xx. Should get exactly the same result because it's the same polynomial. Okay. All right. Since it's not on the homework, I'm not covering the last part of this section, which deals with what if your x values are equally spaced. So in that case, the Newton formula does simplify. It can be written in terms of binomial coefficients, since it's not a homework, I'm not really going to go into that. But I figure time is better spent if anyone has any homework questions.
Not related to homework. In the last class, I'm giving you a talk about rational complexities. You said Van der Waals matrix using that power form.
Right.
You said it requires order n.
Right.
Big operation. I don't really understand what that means.
Well, the big O notation, so it's the same meaning of big O notation as when we talk about convergence. That if I say something is order n cubed, that means the number of operations can be bounded by some constant times n cubed. So in fact, so solving a system of linear equations using like Gaussian elimination takes approximately 2/3 n cubed operations.
How do we know that? Your sense.
What?
How do we know that? How do we know it requires order n? I saw it in the textbook. I memorized it, but I don't understand why.
So like how you find that out?
Yeah.
Okay. All right. I will do that on an example. Let's see. Well, okay. I suppose I wanted to know the operations required by this algorithm. So if you start from the innermost statements and work your way out. So for example, actually here's the only place where there's any actual arithmetic done, so I'll use this one. So this step performs 3 operations, 2 subtractions and a division. Now, the key is how many times does the loop run? This loop goes from n down to j. So the number of times that this loop runs is n minus j plus 1. So this loop requires, just the inner loop here, requires how many operations? N minus j plus 1 times 3. So I have a count for that. But that loop runs n times. So now I need to take that expression, n minus j plus 1, and sum it from 1 to n. Now, that will give me the total number of operations for this whole thing.
Wait, what happened to the 3?
Well, no, sorry, yeah, times 3.
Okay, so you do have to multiply by 3.
Yes.
And from 1.
I'll write it out. Okay, I'll write it out now. So this is algorithm 733 operation count. So that's going to be the sum from j equals 1 to n of a sum from I equals j to n of 3.
Is it n minus?
Well, it goes from n down to j. Well, it's the same as counting from j to n.
Yes.
Yeah. Okay. So this turns out to be, okay, so I already mentioned what the inner sum is equal to. So that's going to be 3 times n minus j plus 1. So now I have to sum this expression from 1 to n. Now, you can use properties of summations that we all learned about in discrete math for that. Now, Beth's broke it up into, I'll factor a 3 out because it's so interesting I forgot to mention it. So I have a sum over j of n minus a sum over j of j plus a sum over j of 1. You evaluate all 3 of these separately. Now adding up n times would give me n squared for this first one. The last one is easy also. I'm adding up 1 n times, so that'll give me n. It's this one in the middle. Whoops. Something went very wrong there. If I'm adding up j from j equals 1 to n, can anyone tell me what that is? Somebody?
N and J.
No.
Okay. Or N plus 1.
Yes. That.
Oh, yeah.
So when you add all that up, and you have your answer. So that's how you do an operation count. It's using these crazy summation formulas. Yeah. I won't ask you to do that on a test. But this, you'll see, it turns out to be order n squared. Generally, the nesting level of loops will almost always tell you what the complexity will be. Like Gaussian elimination has 3 levels of nesting, so it turns out to be order n cubed. Supposedly, Gauss came up with his formula while he was in trouble. He was supposedly he was forbidden from going out to recess as a child, and so he was tasked with adding up all the numbers from 1 to 100. A teacher thinking it would take him a very long time. But he noticed if he wrote the numbers 1 to 100 forwards and backwards and summed the columns, the sum was always 101. So he had 100 of those, so n times n plus 1, but he wrote them out twice, so you divide by 2. So Yeah, seeing patterns like that is what leads to great math, apparently. Okay, there's still time. Homework questions. Anybody?
This is not a homework question, but
Everybody's not homework questions. Okay.
does this fall under the category of dynamic programming? You're filling out a table.
Oh, I mean like divided differences, or
Correct. Does that fall under dynamic programming?
I would say dynamic programming is much too interesting for Vista to fall into that. Be, it's been a while since I've dealt with dynamic programming or seen it in a class. Well, that was like 30 years ago, but like the knapsack problem, I guess.
Yeah, it's been a while
Yeah.
myself, but I remember the core was that you're filling out a table that you later refer to.
Oh yeah. And if the question is like dynamic programming, what is the best way to fill out that table? And relying on that, like for instance, for knapsack algorithm. Yeah, I don't think it just really falls under that category. It's just a convenient notational device. Yes.
Still not homework problem.
Okay.
But I was good because at first you assigned lots of explorations and you cut it down.
Right.
So number 271.7.12 was part of the exploration.
712.
Yeah, and I was already looking at it before we cut it off.
Okay.
Yeah, I did not understand that product notation you used there because
Oh, okay.
because I tried using n equals 3 and n equals 4, I was able to write the determinant in product form.
Uh-huh.
But when using n for n dimensions, I couldn't get this product.
Oh, so it just didn't work out or something?
Yeah, I didn't understand.
Okay. I could check and make sure that there's not a typo in that formula. Oh, okay. So, like, actually, the simplest case of a van der Waals matrix is this one right here, where the determinant is x1 minus x naught. So, for example, in the case of n equal 1, okay, so I goes from 0 to, okay, 0 to 1, and then you have j going from 0 to, okay, so if I is going from 0 to 1, then j is going from 0 to 0 minus 1. Here, that means an empty product. An empty product is considered to be 1.
Okay, so it's that's where I was confused because
Yeah.
at some point it looked as if some of the products was power 0 and everything.
Yeah. An empty sum would be 0. An empty product is 1. So it's always whatever the identity element is. Yeah, and then when j goes to, and then when I goes to 1, you have product j goes from 0 to 0. So 1 factor, and that's where the x1 minus x0 comes in. Yeah. Okay. Now, the one thing that I want to make sure that everybody's on board with, like for this problem right here, is it asks express a system of equations in matrix vector form. So all I mean by that is your unknowns are the a's. So whatever's multiplying the a's are the entries of a matrix. So this will give you the entries in the first row and then the entries in the second row. So you're describing it as a matrix times the vector of a's equals the vector of y's. So that's what I mean by that. So whatever's multiplying the a's are the entries of a matrix. Going from top row to bottom row, and then from left to right, filling in the columns.
Wouldn't those entries be a difference?
What?
Can an entry be a difference?
An entry be.
Well, like I had.
Okay. So not for this problem, but for the next
Oh,
problem.
yeah, that's what I was talking
Yes. So again, whatever's multiplying the a,
about. Right.
however complex it may be.
Okay.
Yeah.
I noticed you answered it in the course website, but I didn't understand 7.2.1.
7 point. 2.1.
Yes, it's so I
Uh,
understand. But it seemed like we're doing the same thing in 7.1.
Okay, so really, since it's already known that the interpolating polynomial is unique, really just want to make sure that this polynomial expressed in this form actually satisfies this condition. Like if you plug in the x's, you get the correct y's.
So are we using values for the x's? Are we using this?
No, I mean, it's general. But you're assuming that that these x and y values are associated with each other, so that really it's about using the properties of the Lagrange polynomial.
Positive for J's.
Like in other words, if I plug in xi here, and therefore plug in xi for x in here, that once I simplify this as much as I can, using the properties of Lagrange polynomials, the result must be yi. But notice the summation involves all the y's. So we need to know that whatever terms involve other y's, other y values, have to go away somehow. So it's like last y standing. But again, it's about properties of Lagrange polynomials. How Lagrange polynomials behave when you plug in a certain one of your given x values. Anything further in the last 4 minutes?
So Canvas says that the quiz is due tonight, and then the website says everything's due.
Right, because I changed the site and I forgot to change the Canvas quiz. It'll still let you submit, so don't worry about that. Basically, it'll show me in big red letters, it's late, and then I ignore that. So. Okay, anything more, even including from down there? Okay, I guess that's it then.